chemistry lesson. Today we'll be discussing electron shells. But last video I forgot to discuss what the nucleus was. And what the nucleus is it's just the region where neutrons and protons reside. That's it really. And of course electrons exist in electron shells, which we'll be discussing today. So to introduce you to this, we'll go over the Bohr model of the atom, which is what you see here. This is pretty much just electrons orbiting around the nucleus as would a planet around a star. This was proposed by the physicist Niels Bohr, and the basic idea is that electrons can only have a limited number of, I suppose you could say, orbits around the nucleus, and they have to have a very specific amount of energy to exist at a specific orbital. So let's say at this orbital here, this orbit, sorry, an electron has to have 2000 units of energy. I'm making these numbers up. And let's say at this second orbital here, it has to have 3370 units of energy. An electron has to have exactly 2000 units of energy to be in this first orbit, but if it can't go there because it's full, then it has to go to the second one, and to do that it has to have exactly 3370 units of energy. The outermost electrons, the ones furthest away from the nucleus, are called valence electrons. Now these are important for chemistry, as these are the ones that hop from atom to atom and pretty much involved in chemical reactions. So outermost electrons from nucleus But why do electrons hop from atom to atom? What's the point in that? Because they're trying to get a very specific, a nucleus is trying to get a very specific number of electrons depending on its period. So hydrogen and helium, the period one elements, so the horizontal rows in the periodic table, are trying to get 2 electrons in their valence shell. The electron shell where the valence electrons exist. However, but the second period is trying to get 8 electrons in its valence shell. Let's discuss the quantum mechanical model now. Unlike in the Bohr's model of the atom, where electrons have a certain energy, have a very defined path around the nucleus, in reality, you can't determine the exact path an electron will take around the atom because of a field of physics called quantum mechanics. This is just a basic chemistry video, so we're not going to get too much into quantum mechanics, although it's interesting in its own right. What you need to know is that this cloud, or in this helium nucleus here, is where the range of positions an electron could be at any moment in time when observed, 90% of the time. And there's also another thing in quantum mechanics called superposition. This might sound weird, but hear me out. When you're not observing an atom, or an electron for that matter, it's in all these positions at once. I'm not going to get too much into that. That's all I really want to say. Of course, 10% of the time an electron can be found out here when you observe it. could be outside this range of positions. This is called an orbital, this range of positions. I'll just write that down. As opposed to a definite, defined orbit, as you would see in a planet orbiting around the sun, or an electron around the nucleus in the Bohr model of the atom. And orbitals really function the same as orbits. To be in a, like you would in an orbit, an electron has to be an exact, has to have an exact energy to be in a certain orbit, to be in a certain orbital, to have the possibility of existing in a range of positions. It has to be, the electron has to be of a certain energy as well. So 2000 units of energy. When an electron's at 2000 units of energy, in the Bohr model of the atom, it's at this orbital here, this orbit here, beg your pardon. In the quantum mechanical model, it's in this range of positions, but we can't tell you exactly where it is unless we observe it. But we can't exactly predict that with 100% accuracy. Only 2 electrons can exist in an orbital at once, but they have to be spinning in opposite directions. So one electron has to be spinning clockwise, and one has to be spinning anti-clockwise. And a range of orbitals of the same energy are called, that group is called a subshell. So I'll just write that down. A group of orbitals with the same energy. All orbitals in the subshell will just be different shapes. That's what distinguishes them. And there's 4 sort of types of subshell you can have. You can have an S subshell, or a P, or a D, or an F. In an S subshell, there is 1 orbital. In a P subshell, there are 3 orbitals. In a D, there is 5. And in an F, there is 7. And an S subshell is just a simple sphere, while a P subshell is like a bunch of lobes around the nucleus. So this little dot's the nucleus. That's 1 orbital. These 2 orbs are another, and these black orbs are supposed to be going in and out of the page. I'm not going to draw the D and the F subshells because they're very complicated to draw. Just bear in mind that these are 3D volumes. These aren't circles. This is a sphere. And these are also, I suppose you'd call them spheroids. Let's say we have lithium. Now I'm going to draw this like the Bohr model of the atom, but think as though I'm talking about the quantum mechanical model. So this is the first energy level, or electron shell even, which is just the electron shell for period 1. So this first electron here electrons want to go to the lowest possible energy. So, and the lowest one available is the 1s. So I'd go to the 1s. you can fit 2 electrons in, so the second electron would also go in the 1s. The third electron, well, the 1s is full, and there's only one orbital in the 1s shell, and there's only one subshell in the first electron shell, so we have to go to the second electron shell, which is all the subshells of period 2. And the next lowest subshell is the 2s, so there we go. Now, the order that electron subshells are filled goes by the Aufbau principle, so I'll just draw you a little thing here. If you're wondering what order the subshells are filled in, that's according to the Aufbau principle. So construct yourself a little list of electron shells like this, electron subshells. So this is in order from lowest subshell to the highest energy subshell. So just draw a straight line. Once the 1s is full, you then go to the 2s, you then go to the 2p, then the 3s, and then you go to the 3d, 4p, 5s, and you just keep on doing this. So this is the order of how you fill the subshells. So once the 1s is full, you go to the 2s. Once that's full, you go to the 2p. Once that's full, you go to the 3s, and the 3p, 4s, 3d, 4p, 5s, so on, etc., etc. We should also talk about Hund's rule. And what Hund's rule says is that an orbital must be half full before you can then start adding an electron to an orbital which already has an electron in it. So let's draw the 2p subshell. Now these arrows just represent the electrons in which direction they're spinning. So up means clockwise, down means anti-clockwise. So if we wanted to add a fourth electron, let's say we wanted to add electrons to the 2p subshell. We've already got one, spinning clockwise. If we want to add another one, we'd have to add it to its own orbital. These little boxes are orbitals. And again, there's 3 orbitals in a p subshell. When you have 2 electrons in an orbital, they sort of repel each other, so they've got slightly more energy. It's not that much. If we want to add a third one, it has to be in its own subshell. And now, if we want to add the fourth one, we would have to start filling up the orbitals completely, then a fifth one, spinning anti-clockwise, and etc. And then if we want to add a seventh electron, we'd have to jump to the 3s electron. The 3s subshell, beg your pardon. What an electron configuration is, it's just stating where the electrons are, in which subshell, and which shell. So we take lithium. A lithium nucleus has a charge of +3. So if we're talking about lithium atom, its electron shells must have 3 electrons in them, cancelling the plus 3 charge from the nucleus out. And we also have to remember that electron shells are filled from lowest to highest, so its first 2 electrons are in the first energy shell, in the S subshell, and there's 2 electrons in that subshell. It's also got an electron in the second energy shell, or electron shell even, in the S subshell, and it's got 1 electron in there. Let's do let's draw nitrogen's electron configuration. Nitrogen has 7 electrons. So it's got electrons in the first energy shell, electron shell, in the S subshell, and it's got 2 there. It's got 5 electrons remaining. It's got electrons in the second energy shell, in the S subshell, and it's got 2 there. Which leaves us with 3 electrons. It's also got some in the 2p orbital, 2p subshell. It's got 3 there. Let's do calcium. Now calcium has, I believe, 20 electrons. It's got 2 in the 1s, 2 in the 2s, 6 in the 2p, and 2 in the 3s, 6 in the 3p, and 2 in the 4s. That might seem long-winded to write all of that out. You can also condense that. You can reference the last noble gas, which is the vertical column of elements rightmost in the periodic table. So we can say it's got, for lithium, we can say it has helium's electron configuration, which is just 1s1, plus 1 electron in the 2s subshell. Likewise, with nitrogen, we can say the same thing. It's got helium's subshell, electron configuration, plus some calcium,